In the projective plane, points and lines play perfectly symmetrical roles. This symmetry leads to one of the most beautiful ideas in geometry, the principle of duality. Let's see what that really means.
Let's start with the axioms of the projective plane. First, any two distinct points determine a unique line. Nothing surprising here. That's true in Euclidean geometry as well. Second, any two distinct lines intersect at a unique point. And this changes everything. In Euclidean geometry, parallel lines never meet. But here, they always do. Natural language can be misleading. It gives different names to what is really the same idea. Saying that a point lies on a line or that a line passes through a point is just two ways of describing the same relationship. So instead, we use a single concept: incidence. We say that a point is incident with a line. Now we can rewrite the axioms in a clean, uniform way. Any two distinct points are incident with exactly one line. Any two distinct lines are incident with exactly one point. Now the symmetry becomes clear. If we swap the words point and line, we get exactly the same statements. Points and lines are perfectly dual to each other, and this symmetry exists precisely because we added points at infinity. There is one more axiom included to rule out degenerate cases. Situations where the geometry becomes too simple. There exists a quadrangle. That is, 4 points, no 3 of which are collinear. It is worth noting that these axioms do not define a single unique plane. In fact, there are many different projective planes that satisfy them. Some of them are finite, containing only a limited number of points and lines. The smallest example is the Fano plane, shown here, with just 7 points and 7 lines. It is easy to verify that it satisfies all the axioms. The plane we are working with is called the real projective plane, and in this world, whenever a statement is expressed purely in terms of incidence, we can swap points with lines and obtain another true statement.
Let's see how duality works on a concrete example. We will take Brianchon's theorem and translate it into its dual form. It is a perfect example because it uses only notions that belong naturally to the projective plane. Brianchon's theorem states the following: if a hexagon is circumscribed around a conic, meaning that all 6 sides are tangent to the same conic, then the 3 diagonals connecting opposite vertices meet at a single point. Let's see how this looks for different arrangements of the sides. And this still counts as a case of Brianchon's theorem, even though the hexagon itself is not drawn directly around the ellipse. What matters is that the lines containing its sides are tangent to the same conic. The theorem also remains true in degenerate cases, such as pentagons, quadrilaterals, and even triangles. But now, let us return to our non-degenerate configuration. Let us formulate Brianchon's theorem step by step, using only the notions of points and lines, and translate each statement into its dual form. To construct the hexagon, we begin with 6 tangent lines to a conic. In the dual world, these tangent lines correspond to points of tangency on the conic itself. This correspondence does not come directly from the axioms. It is an additional geometric relation called a polarity. We will not go deeper into it here. What matters for us is that it works in both directions. A tangent line determines a point, and a point determines a tangent line. From 6 lines, many different hexagons can be formed depending on the order in which neighboring lines are intersected. Let us choose the simplest arrangement, following the order of tangency around the conic. The intersections of neighboring lines form the vertices of the hexagon. In the dual theorem, this corresponds to connecting the 6 points by lines, producing a hexagon inscribed in the conic. Next, in Brianchon's theorem, we connect opposite vertices of the hexagon, obtaining 3 diagonals. These 3 lines meet at a single point. In the dual version, this becomes the following statement: the 3 intersection points of opposite sides of the hexagon are collinear. We have obtained the theorem stating that for a hexagon inscribed in a conic, the 3 points formed by intersections of opposite sides lie on a single line. This theorem is known as Pascal's theorem. Pascal's theorem holds for any arrangement of 6 points on a conic and for any hexagon formed from them. In the literature, the theorem is most often illustrated by a configuration like this one, where the 3 collinear intersection points lie inside the ellipse. By the way, Pascal proved this theorem in 1639, when he was only 16 years old. He published a one-page proof in the form of a poster titled Essai pour les coniques. Nearly 2 centuries later, in 1810, Brianchon, still a student at the École Polytechnique, discovered its dual counterpart, a theorem obtained by exchanging points and lines. Together, these 2 theorems became one of the most beautiful examples of duality in projective geometry. A particularly important degenerate case of Pascal's theorem is Pappus's theorem, known since antiquity and attributed to Pappus of Alexandria in the 4th century AD. It states that if the vertices of a hexagon lie alternately on 2 lines, then the 3 intersection points of pairs of opposite sides are collinear. In projective geometry, this can be viewed as a degenerate form of Pascal's theorem, where the conic degenerates into a pair of lines. Speaking about duality, it is impossible to ignore Desargues' theorem, one of the fundamental results of projective geometry. This theorem has a remarkable property. It is dual to itself. Let us first introduce the terminology. 2 triangles are said to be centrally perspective when the lines connecting corresponding vertices meet at a single point. This point is called the center of perspectivity. 2 triangles are said to be axially perspective when intersections of corresponding sides lie on one line. This line is called the axis of perspectivity. Desargues' theorem states that 2 triangles are centrally perspective if and only if they are axially perspective. The symmetry between points and lines becomes especially clear here. Under duality, central perspectivity transforms into axial perspectivity, and axial perspectivity transforms back into central perspectivity. As a result, the theorem turns into itself under duality, making Desargues' theorem one of the most elegant self-dual statements in projective geometry. First formulated by Gerard Desargues in 1639, this theorem reveals a deep equivalence between perspective from a point and perspective from a line. And that is essentially the idea of duality. The symmetry between points and lines in the projective plane allows us to exchange them in statements and theorems, revealing equivalent twin theorems hidden inside geometry itself. This is the beauty of duality. If you enjoyed this topic, feel free to explore my other videos on projective geometry.